Today I'm going to talk to you about a vLEI shielded pool. Here's the concept. A shielded pool on Ethereum adds a privacy layer using zero-knowledge proofs, allowing custodians to move assets confidentially, hiding who sent what to whom while keeping every transaction verifiable. To access the pool, a custodian presents two verifiable credentials, a vLEI credential, which confirms the legal identity, and an Ethereum key credential, which ties that to their Ethereum address. Once verified, the pool owner grants access, enabling private, compliant, on-chain transactions. This implementation uses W3C-standard VCs and VPs. It could be extended to KERI, ACDC, and IPEX. So let's have a look. The first thing to notice is the pool is empty. We have three tabs at the top here. One is actions the custodian takes on behalf of their customers. The other is actions the pool owner takes, and as you saw, the pool contents. So verifiable credentials and presentations. A VC is assigned to claim about an entity. For example, your vLEI or Ethereum key credential. A VP bundles one or more VCs and proves you control them. You can think of it like an envelope, and you've put in maybe a certificate that you attended university and a certificate that you have done something else. And you hand this envelope over to somebody and they verify it. So let's get some credentials. I'm going to sign a message here to prove that I have this Ethereum key. That's my Ethereum address credential for that address. And there's the signature. Here's a vLEI. Again, this is W3C, not ACDC, so there is a proof section at the bottom here, but the main thing to notice is that's your legal entity identifier and that's your legal name. So what we're saying is Bank of Scotland would like to access our shielded pool. Let's submit that presentation, pop over to the pool owner's screen, and they now have a presentation to verify. So let's do that. And you can see Bank of Scotland now have access to our pool. Moving on. So we're going to look at shielded deposits. A shielded deposit converts your visible ETH into a private note inside the pool. This note represents your deposit value owned by the public key, but hidden from others using shielded pool zero-knowledge proofs. Once created, this note can later be spent or transferred privately within the pool. So let's create a note and a commitment. A commitment is like a hash of the note. So you have a value, 1 ETH, you have their public key. Let's create a note. So here's the data that remains off-chain. So you have 1 ETH, their public key, and a random value. This allows us to tell notes apart. For example, two notes of 1 ETH would look the same if there wasn't a random value. And this is the hash value that will end up in our shielded pool. So zero-knowledge proofs are a way of proving that you know something without revealing all the information. So we need two for the deposit. We need an anti-fraud zero-knowledge proof. And what this is going to do is say, for this hash value, we're going to prove that it contains 1 ETH. The reason we do this is because the user submits this to the contract and the contract can't look inside the hash. So it needs a proof to prove that it's really worth 1 ETH. It's an anti-fraud check, basically. The second one we're going to do is a zero-knowledge proof that proves that the Ethereum key is actually owned by the person depositing in the pool and that their address is in the Merkle tree, which means that they are allowed access to the pool. So we did this with Noir circuits. Noir is a domain-specific language for write-in zero-knowledge proof circuits. It's a lot more high level than what has been available to now, and it's pretty cool. So as you can see here, there's two public inputs. These are visible, the hash value of the note and the claimed amount. And as I said, we do this to prove that that hash actually is the value that the user is claiming, and they do not have to reveal their random value or their public key to do this. So that's quite a simple one. Let's generate that. And this one has a Merkle proof to prove that the address is in the Merkle tree and has access to the pool. There you go. And it also does a proof to show that we have control of that address. So we're going to sign a message to prove that. This one takes a little bit longer than the other ones. So if you're curious, Noir is based on Rust. So if you're familiar with Rust, this will look somewhat familiar. Here we go. The last stage of this is calling the smart contract to deposit the note to the pool and sending along the proofs. So this is going to pop up MetaMask. It's worth pointing out that I'm using Hardhat as my local node, and this account has fake money, so I'm not rich. There you go, there's the transaction hash, and we put this for that into the pool. So let's have a look at the pool. There you go, there's your note commitment, and the next leaf will be 1 because we've started from 0. So now that we have a note in the pool, the next thing is to transfer that note. So the scenario is Bank of Scotland has put a note into the pool for Alice, and we now want to transfer money from Alice to Bob. So this screen looks like it's got a lot on it, and it does, but you do not have to care too much. It's mostly pre-populated from the previous step. What we're going to do is take the input note for Alice, create an output note for Bob, and create a second output note, which is change back to Alice. So shielded transfers, each shielded transfer spends 1 input note and creates 2 output notes, as I said, 1 for the recipient and 1 as private change. All values and identities stay hidden while every transaction remains verifiable on chain using zero knowledge proofs. So this is how we select the note, and it's all pre-populated from the previous stage. The only one that we don't pre-populate is their private key. We don't actually use this, to be honest, so I can just put any value here. If you're wondering why I just typed 42, Hitchhiker's Guide reference. Here's the output note. So Alice is going to send Bob 0.5 ETH. Again, I don't really care what the public key is here. It's just an example. So that's created another note, and the change goes back to Alice. So we need to do one more zero knowledge proof for this, and let's have a quick look. This one's fairly complicated, but again, it verifies a Merkle proof, and this tells us that the note is in the shielded pool. There you go. Then we prove that we know the secret to spend the note. So a nullifier, I won't go too much into that, but it's a way of stopping you spending the same note twice. This is going to prove that we've created the 2 new notes and that the value is conserved. And there's a lot of tests in this. So let's generate a zero knowledge proof of that. There we go. That's the transfer proof there. And lastly, let's spend our note, or spend Alice's note for her. Success. So there's our transaction hash, block number. If we go up to the pool and hit refresh, we can now see that there's 3 note commitments, the original note and the 2 output notes, and you can see that one has been nullified, so that Alice, so we cannot respend Alice's note. I don't have a pretty user interface for this, but I can show you the smart contract reverting. So ping, that's just some HTML issues. And there you go, note has already been spent. So the last thing is a very quick look at the smart contract. So these verifiers are auto-generated from the Noir circuits. So as I said, Noir lets us write zero-knowledge proof circuits in a high-ish level language, and you can generate Solidity verifiers from it. Moving on, this is the deposit function that we called. You can see it takes the note commitment, so the hash of the note, and the 2 zero-knowledge proofs and their inputs. One of the inputs is the claimed amount, and if it doesn't match the amount of ETH sent to this, then we don't let them do it. This ties up the note commitment in ETH. And then we do our 2 zero-knowledge proof verification steps, and we add the commitment to storage. That is a to-do. We need to update the Merkle root. For the transfer one, that took 1 proof and its public inputs. As you saw there, it will revert if the nullifier is there, so we've already spent the note, and we are going to verify the proof again and create the 2 output notes. So that is us, and this video is quite long, but it's actually quicker than my first attempt at it, so hopefully it all made sense.